So for those of you who are familiar with my prior videos and know about my setup and just want me to cut to the chase and summarize data collection and data, I'll take a couple minutes here at the beginning of the video to do the same so you don't have to watch the whole thing. As you folks know, I'm using a Feather Wi-Fi that's talking to Adafruit IO, which is an IoT website, to basically record temperature data above at the soil surface and below a water harvesting basin that's installed in my backyard. For the purposes of this brief summary, I'm just going to talk about the Dallas one-wire temperature sensors installed 3.3 inches above ground, at ground, and at a depth of 6 and 12 inches below ground. So here's basically a graph of the data collected by the Dallas one-wire temperature sensor located about 3.3 inches above ground in that little water harvesting basin. You can see that I've got a linear regression curve there showing that the slope of that temperature increase shows a change of about 17 hundredths of a degree Celsius per day between January and July, which is about 30 hundredths of a degree Fahrenheit per day. And that's just kind of interesting for me to know that that's basically how much temperature increase I'm getting between the fall and the summer through the spring. You'll also notice that I have rainfall events plotted on this graph using those red dots. The depth of rainfall is correlated to the secondary axis. And also notice how those rainfall events do influence the diurnal temperature swings over time, not caught in the linear regression, but rainfall does have an impact on temperature, as you can see in this graph. In the beginning, we had a bunch of rainfall events in January, February, and you can see how that kind of moderated those temperatures early on in the year, and how temperatures also kind of leveled off during the summer months when the monsoons came. So that's kind of interesting. Also notice the wide swing in the diurnal fluctuations for temperature. That's a pretty wide variation and fairly typical of what we encounter in desert environments. And here's the data for the Dallas one-wire sensor right at soil level. And you can immediately see that the diurnal swings are actually being tempered by the thermal mass of the soil. They're not quite as wide, but overall the slope and the increase in temperature is about the same as what's happening about 3 inches above soil. So that's kind of interesting. And now we're looking at data about 6 inches beneath the soil. And you can see that the slope of the temperature increase has flattened out a little bit. Also, those diurnal swings have really mitigated as a result of all that soil basically acting as a buffer for what's going on the surface. So this is also kind of interesting in knowing that about 6 inches beneath ground, I'm getting about 14 hundredths of a degree Celsius increase per day, or 26 hundredths degree Fahrenheit increase per day for this period of interest. And finally, this is what the data looks like for the Dallas one-wire temperature sensor that's buried 12 inches beneath soil surface. You can see that those diurnal swings are almost completely gone in the data set now. However, the slope hasn't really changed between what was going on at 6 inches beneath surface and 12 inches. And what this tells me is that I don't really need a second sensor at 12 inches. It's pretty much mirroring what's going on at 6 inches. So I can probably eliminate this from future data analysis. But still, it's kind of interesting to see how those diurnal swings have really mitigated with that extra 6 inches of soil between this one and the last sensor. Hi folks, so if you've been following my soil monitoring series, you know all about this instrument I developed to support backyard experiments in a little water harvesting basin constructed in my backyard. It's gone through several iterations and improvements over time as summarized in this playlist, but I'll do a quick recap here. The instrument was developed to help me understand soil moisture dynamics using temperature and capacitive soil moisture sensors at various depths in a shallow basin. And this is what the instrument looks like, basically a solar-powered data logger. The instrument includes a Bosch BME280 air temperature sensor located about 28 inches above ground, and both temperature and capacitive soil moisture sensors at various depths. As explained in prior videos, the capacitive soil moisture sensors have been abandoned due to difficulties in capturing the drying profile of my soil, as well as not being particularly robust for field conditions. Also, I learned that this homebrew PVC radiation shield for my BME280 isn't really appropriate for monitoring air temperature. Although there's an air gap between my sensor and this PVC cap, The data I've been collecting suggests the sensor is likely picking up heat from the housing during peak sunlight hours. To remedy the bias, my temperature sensor should be embedded in a properly designed radiation shield like this one shown as part of a Davis Instrument weather station. In response, my own improved radiation shield on my current setup comes from a disassembled Davis station, one that I've been taking apart to better understand how these instruments are put together and designed. And here's the mounted replacement for the layer cake shield assembly, now with my own sensor that I can program and log data with in the field. Prior to attaching and programming the sensor to my existing setup, I ran some tests on the sensor to make sure it was working okay as a standalone piece of equipment. Summarizing those experiments, I realized the greatest difference between both sensors is when the sun is directly overhead, approaching close to 5 degrees Celsius or 8.5 degrees Fahrenheit. Again, this confirms the comments shared by many of you in my prior videos that properly designed radiation shields should help mitigate bias in temperature due to heating of the housing transferring to the sensor. This is especially true when the sun is high on the horizon, but less important in the morning or late afternoon, or for sensors placed in the shade. Now, initially, data collection was addressed using a Feather MO datalogger, which works great for writing data to a camera SD card. Overall, the setup worked great with uninterrupted data logging to a camera SD card, all of which has yielded some interesting results as summarized in prior videos. But I also wanted to take advantage of Adafruit IO, which is a free and powerful Internet of Things or IoT platform hosted by my favorite electronics supplier. In prior videos, I explained how this migration and setup was accomplished successfully using an Adafruit Feather MO Wi-Fi board. I managed to make the transition successfully with live data from all my sensors now reporting out to Adafruit IO. Until recently, I didn't have any issues aside from some power failures associated with a poorly oriented solar panel. Regardless, I've managed to collect tens of thousands of records from this setup. So that pretty much brings us up to date. I just wanted to follow up because to go through all the trouble of designing, installing, and collecting tens of thousands of records merits actually looking at the data to see what it tells us about seasonal variations in air temperature above and within my little water harvesting basin. The following slides do a deeper dive into the data that's been collected with some preliminary results summarized at the conclusion of this video. Let's start with the status of my setup. All right, folks, so here you can see how the setup is doing a year after the fact. So I've got this little basin with some rocks to keep the soil from caving in. You can see that as I trim my bushes, my landscape, I go ahead and I just throw whatever trimmings I have in there just for grins, just to see if I can build up a soil layer. Haven't really been paying too much attention to this until the last week, given a bunch of other projects. And I'll take a few minutes now to summarize what's been going on. The only other addition is now I have this nice rain gauge out here, which gives me much more precise readings of rainfall depth, much better than what I had back there. And this might be helpful in the future, but let's talk about where this project stands. So I'll start by taking a look at the data collected by the BME280, and I'll focus specifically on data collected as of January 20th, 2024 through the present. And I realize the sensor has some bias associated with it, and I'll get into the reason why I'm starting with this sensor first shortly. Dating back to January through mid-July, close to 36,000 temperature records were collected and recorded successfully to Adafruit IO. Of those, only 68 records were bad, reporting temperatures of 180 degrees Fahrenheit for some unknown reason. It gets hot in Tucson, but it doesn't get that hot, especially in January, so these records were deleted. Now you'll notice two data gaps in March, and I recall these were due to a failure of my battery during some consecutive cloudy days, which resulted in me eventually installing a larger battery in the box. Starting on June 30th, I started getting another set of data gaps due to data just not posting successfully to Adafruit IO. Nothing had changed on my setup or network to merit this dynamic. I reached out to Adafruit's forums for guidance, and the bottom line is it may have something to do with my SSL certificate on my Feather Wi-Fi board needing to be refreshed. I haven't attempted this yet, but I'll include a link in the description of this video where you can follow the associated thread. Of greater interest, here are the temperature records for the BMP280, which is the sensor installed under the Davis radiation shield, and thus a little bit more representative of actual air temperature. This one also recorded close to 36,000 records to Adafruit IO, with 48 bad temperature records registered in January and subsequently eliminated. Here I see those same data gaps mentioned before, but I have another one in May. And I believe this resulted from operator error, that means me, in that I was playing around with Adafruit IO data management. And while creating the CSV files for download, I forgot to download one that was subsequently deleted. So that's on me, and it's just something to be aware of, to be very diligent and meticulous in the way you download data from Adafruit IO. And this is just a quick screenshot of what I'm talking about. I'm logged into Adafruit IO right now, and I'm looking at my data. And of course, I'm going to want to download that data, so I click on this blue button. You can see that I have 3 links from prior data downloads. I'm going to go ahead and download as CSV for my latest data that hasn't yet been downloaded. You can see that it's pending there, and I'm going to wait maybe a minute or a few seconds, and eventually I'll click on refresh. Upon doing so, I just lost the last data set that had been saved. It got replaced by the one that I just created. So if that last data set hadn't have been downloaded, I would have lost it. I think that's what happened. Now the question is, what can I do about this data gap, for which I do have records captured using the poorly shielded BME280? I was curious if I could use AI or ChatGPT to help me approximate those results from data that was captured by my other sensors, especially given the significant correlation between these two data sets as demonstrated by this 1 week of data collected in July. Now, in using ChatGPT, I realized that the key is developing a proper prompt to get what you're after, and this is the one that I settled on, and I won't go over all the iterations that I used to get to this. But man, was I blown away by ChatGPT and what you can do with this. It essentially develops code, a Python code that you can modify for your own purposes. It tells you what libraries to import, gives you different methods. You don't really have to know too much about programming to do this outside of being able to understand a compiler and how to import and modify code. Now I should mention that there were various methods that were proposed by ChatGPT to approximate missing data. I went ahead and I stuck with the KNN method, which basically looks at the nearest neighbor of the complete data set to approximate the gaps in your incomplete data set. I thought that might work as a first good try, and just to kind of experiment a little bit with Python programming and ChatGPT. So let's see what happened. So I'll go ahead and include links to the code that was used to do the imputation, but you can see here that this line of code confirms that I'm using the KNN method for the same. Here's a graphical representation of the complete or BME280 data set relative to the incomplete or BMP280 data set. So you can see that I'm missing some orange data points associated with BMP280 here. And this shows the 3,700 plus records that were imputed from the existing data set, thus filling in the blanks. You can see it looks pretty reasonable to me. This isn't too far off from what I would expect to see within that missing data gap. And here's what that filled in data set looks like when graphed in Excel for the entire period that I'm currently looking at within this video. So again, this looks pretty reasonable to me. It's pretty much what I would expect. So that was pretty interesting, using ChatGPT to help me generate some Python code to approximate the missing gaps in the BMP280 data. But I had similar issues with the temperature data for my sensors above, at the surface, and below ground in my little water harvesting basin. So I was wondering if I might be able to use the complete BME280 data set to similarly fill in the gaps for those respective data sets. So first, let's verify there's a correlation between air temperature and soil temperature dynamics. And here you can see the BMP280 data shown in green for a week in July. And the T0 sensor is about 3 inches above soil surface, so it's not surprising to see the respective orange series in this graph, registering high temperatures due to radiation being emitted from heated soil. Similarly, the T33 sensor is right at soil surface, so it also demonstrates a higher temperature via the yellow series relative to the BMP280. However, once we drop about 6 inches beneath soil surface, as shown by the blue line, the diurnal signal is muted, as you might reasonably expect, and at a 1 foot depth, the diurnal signal almost completely disappears. And here I've removed the deep sensor data to make it easier to see the correlation with those higher temperatures slightly above or near the surface of my water harvesting basin. And here's that BMP280 data plotted relative to just those two buried temperature sensors, just to drive home the point that those diurnal fluctuations are muted with depth. Now I know that I could probably approximate the near surface temperature readily using the KNN method, but what about those buried sensors? Their signal's a little bit more muted, so I'm kind of curious as to how that KNN method will play out. So here's the gap for the incomplete T95 series, which is the temperature sensor at about 6 inches of depth. And here are the imputed results. And you can see that the KNN method does capture that diurnal fluctuation, but loses the gradual increase in subsurface temperatures taking place over the course of spring and summer. So there's a slight upward gradient in that deep sensor data that's essentially lost. And here's the gap for the T155 temperature sensor, which is buried at 12 inches beneath ground. And here's the imputed data, once again doing kind of a reasonable job of capturing the diurnal trend, but losing the longer-term increase in soil temperature, as you can see in that jump towards the end of the data set. So yeah, this demonstrates that probably that air temperature is not the greatest for capturing that long-term trend or increase in soil temperature over time. And here's all the data for the temperature sensor located about 3 inches above ground surface in the basin. And you can see obviously there's going to be a lot of variability as things cool off overnight and then warm up during the day. I've plotted rainfall depth based on some rainlog.org data that's been collected in our community, and you can see how rainfall in late January, early February definitely had an impact on the air temperature directly above the soil at the beginning of the year. And then you can also see how in July, when the monsoons came, the overall increase in air temperature kind of flattened out as well. So that's kind of interesting to see in the data. And if we take a closer look at the linear regression for this data, again, highly variable, so low R squared, but you can see that overall we get about 17 hundredths of a degree Celsius increase in temperature per day for this time period, which translates to about 30 hundredths of a degree Fahrenheit per day. So that's just kind of interesting to know how the soil is increasing in temperature as we move through the seasons, or between January and July. And it's also interesting to note that if we look at the temperature sensor that's right at soil surface, that the linear regression basically gives us the same temperature increase profile over time. The only difference is that the variability around that line has decreased a bit because we're getting some buffering from the thermal mass in that soil. And of course, if we go about 6 inches beneath soil surface, now all of a sudden both the slope of that temperature increase as well as the absolute temperature increase per day is going to flatten out, and our variability goes way down. And that makes sense, again, because of that thermal mass in the soil that's buffering those diurnal fluctuations. But there's not much difference if we go another 6 inches deeper in the soil profile in terms of the heating and the absolute increase in temperature per day. This was kind of interesting to me. I thought I'd see a little bit more variability between 6 inches and 12 inches in terms of the slopes and the absolute heating, but that extra 6 inches didn't really make much of a difference outside of eliminating the variability in absolute temperatures. Between January 25th and July 20th of 2024, each feed or sensor that I had installed yield just about 36,000 data points. I did have some intermittent loss of data, which began on June 30th out of the blue. The remedy to fix this was basically just to reset the microcontroller, and that basically brought the connectivity with Adafruit IO right back online. Everything was fine again. I have posted to Adafruit's forums, and they've indicated to me that data loss may be associated with the need to update my SSL certificate, which I haven't yet done. So that's something that's yet to be determined regarding lost connectivity. My own error, or operator error, resulted in about 3,700 records that were lost between March and April for each one of my feeds. And this was just due to me not being very familiar with how to download data from Adafruit IO. And I'm only mentioning this because it's just kind of a warning to be careful when creating new CSVs for download. When you do that, if you've already got 3 CSVs in your queue, the older CSVs will be deleted. So if those haven't been downloaded, you will lose that data, as I did. And finally, I just wanted to mention that all my feeds did occasionally yield bad data posts. For instance, I'd get a temperature of 180 degrees Celsius, which is just not possible for my environment. The bottom line is just be aware of the same when using this hardware, and things you can do are just basically post-process your data or write some error handling into your code prior to saving your data. Okay folks, so I've gone back and uploaded an old sketch that works with a datalogger. You can see I have a little Feather MO8 logger here with an SD card. And I'm gonna try and just replace this because I'm just concerned about losing data. So here goes. All right, here's my old setup. I've tried everything to keep the connection with Adafruit IO up, replacing all the hardware. Just can't seem to get this to work. I did see a post last night on the forum that suggested I should update the SSL certificate. So I'm gonna give that a shot, but for now, I think what I'm gonna do is just replace it with this. And this is the really nice thing about the Feather terminal, is I can just program some other hardware, remove it, and pop it in, and it's just really quick and easy. Okay, first thing I'm gonna do is remove this little JST plug that's coming off the solar LiPo charger. This is already turned off. I should just be able to pull this out now. Okay, so there's the old module. It's just basically the Wi-Fi board plus a Feather OLED. And here's the new one. So this is the Feather OLED with a Feather MO8 logger and an RTC clock. It's the DS3231. Let's see if I can do this one-handed. Okay, let's get this plugged in. Turn this back on. And at last, I've got a little data on the OLED, which suggests that it was able to read the sensors, write something to the SD card. So I'm gonna leave this alone and set up my experiment. All right, folks, so I'm trying to create a no mulch base condition. So all the mulch that I've been accumulating in this little basin over the past year has been removed. This kind of shows you what it looks like, what's been removed from this basin, but take note of all these little bugs that are like hanging out. So all this mulch that's been hanging out here for the last year has created a nice little environment for bugs to help aerate the soil. I can see there's all kinds of activity here from just leaving this alone. And the other thing I notice is this is wet from rainfall events that we've had over the last week. I bet if I come back later this afternoon, now that I removed all this mulch, all these little bugs will be gone and this will be bone dry. So, chalk one up for mulch. I think it really helps in situations like this. Alrighty, so the system's been reset, and in addition, I have this really nice rain gauge now that's going to give me some precise measurements on rainfall impacting this little basin, so I can compare one rainfall event to another and the impact that that has on soil temperature. So that about does it for this chapter. I've been collecting data for the last couple weeks. I'm real curious to see how that basin performs in regards to temperature with and without mulch. So if you're interested, please consider subscribing for updates, and we'll see you next time.